Sorry about starting late, but okay, this is recording. So, the chapter 22 homework is due on the 3rd. The chapter 23 homework is due on the 10th. The chapter 22 quiz will be on Wednesday in SI. And the chapter 23 quiz will be online on Blackboard from that Wednesday until the next Thursday, the 9th. Because we're having the test the next week, so the scheduling just doesn't work out. So it's online. You'll have a week to work on it. Let me get, okay. Why is everyone late today? So Jackson, you're here. And Eric, you're here. Everyone after you will be late. So the chapter 23 quiz will be on Blackboard because the schedule works out such that there's like time before the test for you to do the quiz. So I put it online. And Monday the 6th will be the first exam. It'll be multiple choice, mostly with a few short answer questions. It's 100 questions, but people have not had trouble with it in the past, so don't worry about it. Yes, you still get a sheet of notes for reference, just like you do on all the quizzes. I just didn't have room on this page to put that. But you will get a reference sheet just like the exam. The chapter 23 quiz will be online because there's not enough time before the exam. And if I push the exam back, I might not have had the exam before midterms, so it's a scheduling issue. Yeah. And lastly, we have a lab today. Yes. What? Yes. I just didn't have room to put it on this current announcement page because you can see it's very full. It'll be up on Wednesday that you get a sheet of notes, but you still get one sheet of notes, double-sided like you do on the quizzes. Same idea. And the exam is mostly multiple choice. Yeah. Any other questions? I'm going to get started. So we were talking about weathering. Chemical weathering is most rapid in areas with high temperature and abundant moisture. In very cold areas like polar regions and very dry areas like deserts, chemical weathering is relatively sluggish. It's slow. Okay. So this is a short video about chemical weathering. Chemical weathering is
the second kind of weathering is called chemical weathering. Chemical weathering causes changes in the rocks from the reaction of different chemicals on the surface of the rocks. One common example of chemical weathering is called oxidation. If we were to leave an iron nail in a cup of water for a few weeks, a chemical change takes place. The nail gradually becomes coated with a dark red substance we call rust. Rust is oxidized iron. Here we see the difference between a shiny new nail and an oxidized nail. This rusting or oxidation deteriorates any surface on which it reacts, and will eventually cause it to break down and fall apart. The mineral iron is present in many different kinds of rocks, and oxidation can break down these rocks if they're exposed to water for long periods of time. But are there other ways in which rocks can chemically weather? These rocks are covered with a plant called lichen. They illustrate another example of how the chemical weathering process takes place. The lichen actually secrete a mild acid which can dissolve or eat away the surface of the rock. Carbonic acid, a mild corrosive agent, can form when water and carbon dioxide combine naturally in the air or below the earth. Underground caverns like this are one of the most spectacular examples of the effects of weathering caused by carbonic acid. This cavern started out as small openings below the Earth's surface where water seeped in. The water combined with carbon dioxide from decaying plant material in the soil to form carbonic acid. As this acid dissolved the rock around it, the pockets gradually grew in size. The force of gravity, combined with underground streams, carried the dissolved rock fragments away until finally a huge cavern was formed. This, along with the continuous seeping water, caused the cavern formations to grow even stranger as time passed.
Okay. So that's chemical weathering. So certain rocks and minerals are more resistant to chemical weathering. Certain rocks dissolve or break down chemically more easily than others. And you can observe this by viewing cemetery headstones. So marble headstones are composed of the same mineral as limestone, calcite, and therefore they readily react with slightly acidic rainwater. While granite is much more resistant to weathering because the minerals it's made of don't readily react with slightly acidic water. So here's sort of a summary of weathering. Weathering is the breakdown of material into smaller pieces, or there's mechanical disintegration, which breaks a mineral or a rock into smaller pieces without changing its chemical makeup. There's frost wedging, where freezing and thawing water in cracks breaks things. You can have salt crystal growth, where salt crystals growing in a crack can break things apart. Mechanical exfoliation, where rocks expand and crack as the overlaying rocks get removed by erosion. Basically, as pressure is relieved, the rocks expand, and this causes them to crack and break apart. They sort of look like onions. They get layered appearances. Root penetration, powerful tree roots can grow in rock fractures. Thermal expansion and contraction. Rocks will expand and contract with temperature, and that can cause them to break apart. Abrasion, when rocks and minerals collide in a moving current, that can wear them away. And then there's chemical decomposition, where changes of the chemical composition of rocks and minerals. You can have dissolution, where soluble compounds like limestone get dissolved, and this produces caves. Oxidation, mineral ions combine with oxygen to form an oxide. This forms rust and causes reddish rocks. And hydrolysis, where H+ ions displace other ions to form a different mineral. This is common with feldspars. It's the process that turns feldspar minerals into clays minerals. Now, once material has been weathered, it is eroded. It moves from where it formed or where it was broken off a rock to somewhere else. So erosion is the downslope movement of soil and rock due to gravity and various geologic agents. The most common agents of erosion are gravity, which is mass wasting. This is stuff rolls down the hill. Streams, glaciers, wind, and waves. As you can see, the most common thing driving erosion is water. followed by wind, and then stuff sliding down the hill, just gravity itself. So wind and water erosion are the most common types. So here's a short video about wind and water erosion.
The landscape of Earth has been formed over millions of years, and it is constantly changing. Some changes are major events that you can see happening, like volcanic eruptions and earthquakes. Other changes to Earth's surface are happening so slowly that you cannot notice them from day to day. One such process is erosion. Erosion happens when rock or land changes shape over time. There are different types of erosion. One type is wind erosion. You may not think that wind can change the shape of Earth, but this has happened in many places. One location that has been shaped by wind erosion is in the southwest United States in Arizona and Utah. This area is known as the wave because it looks like an ocean wave crashing. But how did it get this shape? Wind blowing through the desert carries sand along with it and blows across the rock. This wears away small amounts of the softer rock, and over a long enough time period, the wind creates unusual shapes in the rocks. This area of Utah, called Monument Valley, has some of these unusual rock formations caused by wind erosion. As the rock has been worn away, it has left behind tall structures like these totem-shaped rock pillars. Wind erosion is common in areas of land that are higher in elevation, such as these formations, also in Utah. Another common type of erosion is water erosion. This occurs when water causes rock or land to change shape over time. One of the most dramatic examples of water erosion is also found in the United States. The Colorado River flows from Colorado to Mexico. Over millions of years, the water traveling this path created a canyon. This canyon is now called the Grand Canyon and is a well-known tourist attraction. The canyon is a mile deep and up to 18 miles across at its widest areas. This amazing sight was shaped entirely by the water running over it day after day. Another amazing example of water erosion can be seen along the coast of Scotland, where you will find a rock formation known as the Old Man of Hoy. In the same way that river water can erode rock, ocean waves hitting the land again and again can also cause erosion. This particular formation is called a sea stack. It is a large column of rock that is left after wind and waves erode the surrounding rock and cause sections of the cliff to completely collapse. The Old Man of Hoy is almost 450 feet high. You can figure out if erosion is caused by water or by wind in a simple way. If there is a water source there, like a river, a waterfall, or an ocean, then the erosion is due to water. There are beautiful examples of wind and water erosion all over the world. Many of these locations are popular tourist destinations, while others are rarely seen. Maybe someday you will see one of these wonders for yourself.
Just quickly. John, right? NF, oh, sorry. So, the first thing that causes erosion is runoff. You've seen runoff. Anytime you've seen, rain running across the ground, it rains and then there's water running across the ground, that's runoff. When rainfall exceeds the amount of water that can be absorbed by the ground, runoff of the excess water occurs. You see a lot of that in cities because we've made much of the ground not penetrable. So as this water flows over the surface of the ground, it can be particularly erosive in areas where there is vegetation to hold the ground in place, like a freshly plowed field, or empty lots, things like that. And runoff usually only occurs over short distances before it either soaks into the ground or empties into a stream. Basically, runoff will either soak into the ground, or it will eventually, enough water will collect to at least form a temporary stream. So it'll become part of a stream. Now, a stream is any channelized flow of water occurring between two well-defined beds. So this is everything from some thin, tiny stream running across your backyard or across a backyard up to the Mississippi River. So to a geologist, the size of the channel flow doesn't matter. Both the Mississippi and a small mountain brook are considered streams. So if you have like a little brook behind, or a small mountain brook, that's a stream, but so is the Mississippi River. That's a big stream. And then as a stream flows, it carries material with it. So other material gets transported by the water. This is called the stream load. Stream load comes in three parts that are organized by their size and how they are carried. So the particles in the stream load vary from, at the smallest, dissolved material that's just dissolved in the water, to fine particles, to large rocks. And the stream load at any given location or time depends on the stream's gradient, its slope, its volume, how much there is there, its current velocity, how fast it's moving, and what the channel is made of. And usually the stream load is divided into three components according to how it's carried in the stream. These are the dissolved load, which is dissolved in the water. So if you took the water out of the stream and let it settle, the dissolved load would still be in the water. The suspended load is suspended in the water. This is like muck in the stream that makes it brown. So lots of rivers and streams and stuff are brown in color because they're carrying particulate matter in them. The suspended load, if you take the water and set it, would settle to the bottom. So the suspended load is being carried in the stream, but it's just suspended in the water. If the water stops moving and has time to settle, it will fall out. And then, the dissolved load will not leave the water unless it evaporates. And lastly, the bed load are larger bits of material that bounce along the bottom of the stream. So if you just collect like a jar of water from a stream, it's not going to have any bed load in it because the bed load is all on the bottom of the stream. So the dissolved load consists of minerals and elements carried by the stream in solution, and up to 20% of the stream load could be this dissolved portion. The suspended load consists of fine to medium grain discrete particles suspended in the flowing water. These are like silt and sand and stuff. And the suspended load will change dramatically depending on how fast the water is moving. The slower the water is moving, the smaller the particles it can support. The faster the water is moving, the bigger the particles it can carry. So fast moving streams carry more suspended load. And then the bed load is larger grains that roll or bounce along the bottom of the channel. And here's a video showing stream bed load in Alaska. These pebbles and stuff bouncing along the bottom, that's the bed. This stream doesn't have much in the way of a suspended load, probably because it just formed. This is in an intertidal area, so it's like on the beach. So it hasn't picked up that much sediment. It hasn't traveled very far. But you can see that these are all rolling along on the bottom. And some lighter stuff being saved. Yeah, the gravel is the best. And you see like sand and silt really in the stream itself now. And there's certainly evolved quite in that. So, when you have a stream, that water carries stuff away and it's going to basically dig a channel. In the upstream portion, you get that water will basically dig down and you'll get a V-shaped stream valley. But eventually you'll get to more or less the level the water wants to be at, the level that corresponds with where it's draining out, roughly. And once it reaches the level of some standing body of water that it flows into, it's not going to erode any further down because there's no, the water isn't going down anymore. It's just going sideways. And thus, once you hit level land, the stream will start eroding on its sides more than its bottom. So streams that empty into a lake will have the lake level as their lowest possible of erosion. Streams that empty into the ocean will have the sea level as their lowest level that they can erode. This is the base level, the current limit below which a given stream cannot erode. So around here, that's going to be the level of the lake, mostly. Unless the stream is being fed into the Mississippi, as a bunch of stuff is, because the hydrology around here has been heavily manipulated. And then, yeah, but it's roughly the same level. And this is usually sea level. So how the Grand Canyon got formed is that whole plateau had a bendy stream on it, and then the whole thing got pushed up. And so that stream was able to carve straight down. So in a downstream portion of a stream, the level that flowing water begins to approach is the ultimate base level. So it starts to erode more on the sides of the stream than the bottom of the stream. The downward erosion slows, and most of the stream's energy is expended side to side as it erodes side to side. And during flooding, the stream will overflow its bank and deposit sediments over a wide area. You get a widened flat valley called a floodplain that develops, that's sort of carved out by the stream as it sort of meanders back and forth through this floodplain. So here is a short video about floodplains. And they're more important than ever because we're having more flooding than ever. We're having more rain because of climate change.
Wyoming is a mostly arid state, but many of our communities are actually built in low-lying areas adjacent to rivers and streams, known as floodplains. Floodplains are a natural part of a river structure, and during high flows, such as spring runoff, rivers will exceed the normal channel capacity and flow across the surrounding land, the floodplain. People have built in and near floodplains throughout history. In the past, rivers were important corridors for transportation and trade. Because they receive periodic high flows that often carry lots of sediment, floodplains have excellent soils and agriculture thrives in floodplains. In order to accommodate human uses, floodplains are some of the most altered ecosystems in Wyoming. The natural processes that make floodplains valuable to humans, attractive to wildlife, and highly productive also make them hard to manage. Channelizing streams and draining wetlands in the floodplain make these areas easier to develop, but many of the benefits such as soil formation are lost without periodic flooding. People living in floodplains should understand that no matter how these areas have been altered, they will still flood at some point in the future. The Federal Emergency Management Agency, FEMA, provides maps and resources for people living in floodplains. Your local extension office has additional resources to help you understand floodplains and also to assist with disaster management during floods. For the University of Wyoming Extension, I'm Milton Geiger, exploring the nature of Wyoming.
We're in the middle of a floodplain. Yeah. Most of Chicago is. Oh, why are you not? There. So, new sediments that are received periodically within the floodplain make these areas some of the most fertile agricultural land in the world. And the rich soils most lead to most floodplains becoming heavily populated. And even though they have usually a quiet appearance, floodplains are still prone to periodic flooding, and this can cause significant damage to crops and structures. Now streams meander. In downstream portions, the stream will tend to twist and turn, making loop-like bends that are called meanders. So what happens is the stream will always take the path of least resistance, and that'll create a little bit of a bend. Once a little bit of a bend exists, any bend will actually become bigger and more exaggerated, because on the outside of a bend, water will travel faster, while on the inside of the bend, water will travel slower. Which means on the outside, there's more erosion, and on the inside, there's more deposition of material. And that causes the loops to get bigger. Eventually, they can run into each other and get cut off, and the entire loop gets cut off. You get what's called an oxbow lake. So here is a video showing an animation of the formation of an oxbow lake. Now, as the stream forms, on the outside of the curve, the water is moving faster, so it erodes more, while on the inside, more is slower, so stuff is positive. The curve just did. The outside, getting faster, the road is down. They come close together, and eventually cut off. Once it's cut off, water will flow this way to an oxbow lake. It'll eventually go away and leave behind a marking. So here is a stream meander with an oxbow lake. You can see the former parts of the stream. There's another one over here. You can sort of see the whole meandering stream. So at every time a stream floods, it will actually build its banks up higher from depositing material. So streams erode and transport enormous quantities of material. And most of these sediments will eventually end up in the ocean, where the stream ends. So for example, the Mississippi River carries 500 million tons of sediment into the Gulf of Mexico each year. And this is steadily building out the state of Louisiana. So most of these sediments accumulate at the mouth of the stream as the stream velocity significantly diminishes, because the ability to carry sediment is dependent on how fast the water is flowing. Once it hits the ocean, it slows way the heck down, falls out of the water, and forms the stream's delta, which is called a delta because it's triangular shaped and it looks like the Greek letter delta, the capital Greek letter delta. So here's a video about how river deltas formed and other depositional landforms.
Okay, Houston, we've had a problem here. This is Houston. Say again, please. Houston, we've had a problem.
Hey Houston, we are learning how the earth is sculpted by water, and fancy term, depositional landforms. We're going to be learning about sediments and where they get deposited, and then what kind of a landform they create. The most simple one is called a sand or a gravel bar. And a sand or gravel bar, what do you think is going on? Is as a river deposits sediments, it can create a little bar, a sand bar. You'll see this out in Galveston. In many ways, Galveston and that whole area is a sandbar, is what it is. The second one is called a delta. Now, the deltas are named after the Greek symbol delta, and a delta is a triangle. I'm not sure if you can quite see this, but this takes the shape of a triangle. The river is meandering here, and then he snakes out here and here and here, because ultimately what you're looking at right here is that these are sediments. So that maybe the mouth of the river was back here many, many, many years ago, and now it's depositing in the shape of a triangle, sort of spreading out. And how does a delta form? It forms actually in stages, right? The first stage is you get a nice, pretty channel, but then as that sediment deposits, then the channel, all this sediment gets deposited here, it shifts over here. And then, of course, it shifts over here because all that it gets cut off because it fills in with sediment, and then we get a new snake. You see how it kind of is growing as time goes on because it deposits sediments. The sediments then create a little natural dam, and then the water says, oh, I got to find a new way, so it, boom, shoots out another way, and that's how a delta forms. And here's a cool picture. I mean, the Mississippi River, not far from where we're at, right? And this is the Mississippi River Delta, that down near New Orleans and all that kind of stuff right here. We've got the Mississippi River, and it's been this delta that's formed over many, many years. And even you've got this river, which is actually part of that whole Mississippi River system. Right now, this Mississippi River is extending way out here, and then we can start seeing the new delta. And notice you can see the sediment. This the white piece down here tends to be, well, not is, tends to be, it is filled with sediment, and it's like making the ocean shallower because they're depositing sediments, thousands of cubic feet, millions of cubic feet of sediment down out into the Gulf of Mexico. And now part of this section goes to an interesting comment, is that how do we form a natural levee? A levee is like a dam, right? It's something that's going to cause it to happen, because as water flows during a flood, right? So you got a flood. What happens is the coarse sediments, the bigger pieces, they don't travel as far, and so they create they get deposited, the big pieces of rock, right, on the edges. And then when the water recedes, the flood goes down, then you've got a little natural levee. And then it floods again, you see, right? It floods again, and more coarse sediments. And you see how the natural levee, it's naturally. So this happens on a natural basis. After many floods, you're going to get sort of more like steeper banks of your rivers. So that's how a natural levee forms. And then lastly, we want to talk about something called an alluvial fan. I think this is a super cool picture. Is what you've got is you have this is a picture, right? This is in a river, now, but this is going to happen, and it creates this, you can see the fan-like appearance. Alluvial fans are kind of like a delta, but it happens when you're going to have super steep land followed by, so this is like a big mountain. So instead of like the Mississippi River that is flat where it's reaching the ocean, this is a big mountain, and then all the sediments get dumped in really, really fast because they're coming crazy fast from the super steep slope, and it makes an alluvial fan. Again, crazy short stuff. Streams, water, the world is sculpted and changed by water. We'll see you in class.
So, we talked about how liquid water moves things. Well, solid water can do it too. So a glacier is a large mass of ice that covers part of the Earth year-round. So they consist of recrystallized snow, and they flow over the surface of the land under the influence of gravity. So in general, glaciers form from regular snowfall in certain places. It gets recrystallized, they flow down, and they melt or fall into the ocean or whatever somewhere else. So much of North America was covered by glaciers over 10,000 years ago. That is in fact why this area is so damn flat. It got scraped flat by the glaciers. There are still about 1,100 glaciers within the lower 48 states, primarily in mountainous areas. That's where you get glaciers, because it has to be a place where more snow falls than melts each year. So basically, the rate of snowfall has to be higher than the rate of snow melt. And so that happens in the mountains. And approximately 3% of Alaska is covered in glaciers. Nearby large glacier place is Greenland. Greenland is mostly covered in glaciers. The center of Greenland is all covered in glaciers. And then Antarctica is all covered in glaciers, pretty much. So a glacier will form in an area where over a number of consecutive years, more snow accumulates than melts. Basically, you get more snow coming down than actually melts. When enough snow builds up, it will compress and recrystallize into solid ice, glacial ice. So glacial ice has a lot of air and stuff trapped in it because it's just compressed, recrystallized snow. So it's actually kind of different than the kind of ice you make in your freezer. But eventually that glacier will begin to flow downhill due to its own weight, because it's really big and heavy. And most of the icebergs in the ocean are large chunks that have broken off of the edges of glacial ice sheets of Greenland and Antarctica. And glaciers are changing due to the increased air and ocean temperature. Generally, they are shrinking and melting faster, which is not necessarily a good thing. So, there are two main types of glaciers. There are continental glaciers and, well, they're called alpine glaciers, but they're mountain glaciers. Continental glaciers cover most of Greenland and Antarctica. That's where we find continental glaciers. They are massive, thick ice sheets that cover large portions of a continent, or large portions of land. Now, smaller glaciers are the alpine glaciers. So you can have cirque glaciers are one type. These are much smaller. They can be found in mountain regions located in hollow depressions that are protected from the sun. Most of the glaciers in the US are cirque glaciers. And as the glacier flows, it'll carve out an amphitheater-like depression that's called the cirque. And as the ice melts, these glacial depressions fill with water and get called cirque lakes. There are also valley glaciers. So a cirque glacier is this like depression that fills with snow and forms a glacier. And then the glacier often flows out to feed into a valley glacier. Valley glaciers occur when an entire valley is covered with glacial ice that flows down the valley. And the flow rates of glaciers depend on a number of factors and vary from centimeters to meters per day. And eventually, at lower and warmer elevations, the glacial ice melts and feeds into streams. And if the rate of flow and the melting rate are equal, the glacier appears to be still. It's actually moving. New glacier is formed at the top. It flows down and melts at the bottom. But those are the big differences. So you have valley or alpine glaciers, cirque glaciers feed into them. Those are sort of the mountain glaciers. And then there are continental glaciers like that cover Greenland and Antarctica. So here is a short video classifying glaciers.
Ancient glaciers have contributed to the formation of some of the most spectacular landforms on Earth, while modern examples provide data to help us figure out changes to our climate.
In today's video, we will start with the basics and discuss some of the most common features of two major types of glaciers.
A glacier is a long-lasting mass of slow-moving ice and snow. For a glacier to form, we need an environment where cold temperatures dominate for most of the year. Consequently, most glaciers are either found in polar regions or at high elevations on the continents.
We recognize two basic types of glaciers. Most of the world's ice is preserved in two massive ice sheets found in polar regions.
In contrast, high mountains on most continents are home to smaller alpine glaciers, also known as mountain or valley glaciers.
We'll begin with a closer look at ice sheets. Let's start with the obvious. Ice sheets are huge, extending for millions of square kilometers. Such large volumes of ice and snow can only accumulate and remain where temperatures are very low.
For example, Antarctica is the coldest place on Earth. Average annual temperatures in the high interior of the continent are about minus 57 degrees Celsius. Even areas along the coast rarely get above freezing during the year.
To cover such a large area, ice sheets must also be very thick. There are several kilometers of ice sitting on top of Greenland and Antarctica. Consequently, the ice sheet covers every landform, with the exception of some particularly tall mountains.
Glacial ice flows from the thick interior of the ice sheet to the thinner margins. You will have noticed that Antarctica is surrounded by ocean. A glacier that ends in the ocean may be known as a tidewater glacier.
There are many glaciers that flow off Antarctica and terminate in the ocean, where the ice can form floating ice shelves or break off to create icebergs.
Ice sheets contain ice formed recently, but they also have layers of ice that were formed up to hundreds of thousands of years ago. For example, some of the ice layers at the base of the Greenland ice sheet may be more than 100,000 years old.
The thicker ice on Antarctica extends even farther back in time. The European Project for Ice Coring in Antarctica has drilled the oldest existing ice core, which contains 800,000-year-old ice from a location in Antarctica known as Dome C.
Scientists can interpret the ice properties to figure out how temperature has fluctuated on Antarctica throughout that time. The record reveals a sequence of long cold periods separated by shorter warm episodes.
For more information about the relationship between the global distribution of ice sheets and variations in climate, watch our Ice Ages and Climate Cycles video.
Outside of polar regions, alpine glaciers form at high altitudes in modern mountain ranges on every continent except for Australia.
Alpine or valley glaciers typically begin in a permanent snowfield at high elevations. For example, the Aletsch Glacier is the longest glacier in Europe and begins at an elevation of just under 4,000 meters in the Swiss Alps.
Let's take a closer look at some of the features of this glacier. More than 2,000 meters below the summit, temperatures are much warmer and cause the glacier to melt and supply water that then fills this substantial reservoir.
Traveling about 5 kilometers up the valley, we come to the end of the glacier where solid ice is buried under sediment at the glacier terminus. This sediment, a mix of large boulders, sand, and clay-sized particles, is largely derived from material breaking off or eroding from the valley walls.
We can follow this sediment a little further along where we notice these dark bands, known as medial moraine, that transport sediment along the glacier.
Notice the bathtub ring-like feature along the valley sides, indicating that the glacier used to be larger and thicker and occupy more of the valley.
Zooming in on the surface of the glacier, we can see cracks in the ice, known as crevasses, that form above locations where the base of the glacier moves over a step in the valley floor.
Continuing along, we see that the glacier we have been following is actually made up of ice from several smaller tributary glaciers.
These smaller glaciers flow out of steep-sided hollows known as cirques that form just below the ridge crest and serve as a supply source for the glacier. Notice that unlike the rest of the glacier, the cirques are snow-covered.
The overlying ridge is topped by a couple of pointed horn-shaped peaks characteristic of alpine glacial landforms.
Drawing back, we can see the full extent of the glacier from its beginnings in the high cirques to its terminus, 24 kilometers further down the valley.
Alpine glaciers are much shorter and thinner than ice sheets. They tend to move more slowly, and the age of the ice flowing through these glaciers is more likely to be measured in hundreds of years rather than hundreds of thousands.
Not all alpine glaciers are as impressive as the Aletsch Glacier. Some are much smaller, like the Cirque glaciers and the Chugach Mountains of Alaska.
Some glaciers expand as they exit a valley to form wider Piedmont glaciers, like the Malaspina Glacier in Alaska.
We have 3 learning objectives for today's lesson. How confident are you that you could successfully respond to each objective?
So this is a valley glacier. You can see it's running through a valley. And it probably starts at a Cirque glacier. Now, as glacier flows, it'll loosen and carry away eroded rock material, much of which is eventually ground up. And though they're slower, much slower than the streams, they're not as selective and are able to pick up huge boulders and gouge very deep troughs. And glacial erosion, unlike streams, causes deep U-shaped valleys instead of sharp-sided V-shaped valleys. And the material that's been transported and deposited by glacial ice is called till, or glacial drift. But till deposits are generally not well sorted or layered. They're because, so material carried by streams gets sorted because the heavier stuff falls out first and the lighter stuff falls out later. But that doesn't happen with glaciers. Everything falls out when the glacier melts. And at the sides and ends of a glacier, you can get ridges of till that are called lateral and terminal moraines. These are like piles of material left behind. At the end, or terminal moraine marks the furthest point the glacier advanced. And terminal moraines can be found as far south as Indiana, Ohio, and Long Island, New York, from the glaciers that covered this area back in the last ice age. So you can see as the glacier flows down, it drops material out and that piles up to form moraines. So these are end moraines. This is the terminal moraine. And these are some recessional moraines that you get as you recess backwards because more was melting than was being added. Now, wind erosion. Wind erosion is very slow. It can be a significant process in desert areas because deserts don't have a lot of water. They're defined by a lack of precipitation, but they can be in any temperature range. There are hot deserts, there are cold deserts. That the definition of a desert is just dry. Technically, Antarctica is a desert. But in most deserts, because they're so dry, if you have a thunderstorm, every once in a while they'll get like a thunderstorm or a big dump of water, and that can produce tremendous short-term erosion. And you get these flash floods that are honestly shocking to see. But during most of the year, the prime erosional agent in a desert is the wind. And a really dramatic case of wind erosion was the 1930s. In the 1930s, there was the Dust Bowl. Basically, the whole western part of the country, we'd removed all the vegetation that had held all the soil down and loosened it all up by farming. And then there was a long period, dry period. And basically, millions of tons of topsoil blew away in what was called the Dust Bowl in the 1930s. So wind-blown topsoil. It was really bad. And it coincided with the Great Depression, so that added extra awfulness. Another form of erosion is mass wasting. Mass wasting doesn't have an extra agent to carry it. It's just stuff rolling down the hill at some level. It's just the general term for downslope movement of rock and soil under the influence of gravity. Gravity tends to pull material downslope. Friction tends to keep the material stationary. It is greatly affected by water, however, because water is heavy. If you've ever picked up a gallon of water is heavy. And if enough water enters soil, it can reduce the friction. So in general, the addition of significant water adds weight to the material and also reduces the friction between the particles. So generally, the presence of water promotes slope failure. It's a little more complicated than that. Turns out a little bit of water increases friction, but any significant amount of water decreases friction. And you may have experienced this if you were building a sandcastle. You used wet sand because it stuck together better than dry sand. But really wet sand just collapses, because it turns out the stickiness of particles with water is complex. But as a general rule of thumb, extra water adds weight and reduces friction. So mass wasting can be divided into two big categories: fast and slow. Fast or catastrophic mass wasting comes in two basic forms. So fast mass wasting is sudden and dramatic. You could have landslides, which is a bunch of rapid downslope movement of large blocks of weathered material. If large volumes of rock are involved, it's called a rock slide. But a landslide is just stuff comes loose, rolls down, but it's solid. And then there are mud flows. That is where material basically gets so saturated it turns into mud and just starts flowing like a stream. So it's the rapid downslope movement of soil that's become unstable due to the absorption of large amounts of water. So it's this big flow of mud downslope. And landslides and mud flows move differently. Landslides are material tumbling down. Mud flows flow like a stream. So this is a mud flow. You can see how the mud sort of flowed down the hill, empty out, flowed down the hill and out, sort of along the path of least resistance there. While a landslide would just be the rocks would fall straight down or more straight down and less flow-like. Now, slower mass wasting are things like slump, which is the relatively slow downslope movement of basically what is a big unbroken block of material, where you have some block of material and it slides slowly down. Slumps will leave a curved depression in the slope, marking where the block detached. And then the slowest form is creep. This is the very slow, imperceptible particle by particle movement of debris down a slope. Basically, as things warm and cool through the day, it causes particles to move outwards and then down and then outwards and down, and they sort of creep down a slope. It's far too slow to see the actual movement. The result of years of creep can be seen along slopes. You'll see things tilt over, trees growing in funny shapes, things like that. And abundant vegetation and roots help deter all types of mass wasting. So here's a short video about the different types of mass movement.
Mass movement is the movement of surface material downhill due to gravity.
Mass wasting.
The loose surface material is known as regolith. There are four main factors which influence mass movement: gradient, the steepness of a slope; water, this is generally in the form of rain, making the regolith heavier and more unstable; human activity, such as the building of roads and railway lines which undercut a slope; and vegetation, The roots of trees help to bind the soil together to make it more stable.
And the roots of most.
Soil creep is a very common form of mass movement and can be seen in the landscape all around us. Any second now. Still no? That's because soil creep is a very slow form of mass movement, often as slow as 1 to 2 centimeters per year. Similar in a way to the movement of tectonic plates, you cannot see the movement, but can see the impact of soil creep over time. Tree trunks bend and telegraph poles lean downwards. Fences may collapse and walls can have soil build up behind them before eventually bulging and collapsing. On grassy slopes, the soil may form at the steps known as terracettes. As soil creep bends the lower trunk of a tree, it will begin to lean over. However, the trunk will then straighten as it continues to grow upwards. This is to maximize the amount of sunlight that the tree receives. Landslides occur when loose rock and soil move down steep slopes in upland areas. The removal of vegetation and the undercutting of slopes to build roads and railway lines can combine with heavy rainfall to lead to a landslide. A landslide scar is often left behind as the surface layer of soil and grassy vegetation can be removed. Like other fast forms of mass movement, landslides can cause significant damage and destruction to animal habitats, farmland, and human settlement. Mud flows are a very fast form of mass movement. They can occur in areas of high rainfall with steep slopes where vegetation has largely been removed, such as on farmland in the west of Ireland. Heavy rainfall can make the soil saturated and unstable, creating a fast-flowing river of mud that can flow freely and travel several kilometres downslope. Bog bursts are similar to mud flows, but occur in upland areas where peat is found. A lahar is a volcanic mudflow and generally can lead to more casualties in an area surrounding a volcano than lava. When volcanoes are active and erupting, they produce a tremendous amount of heat. If the summit of a volcano is snow-capped, the snow and ice will melt. This will mix with the volcanic ash and soil on the mountain to form a volcanic mud flow. The Nevada del Ruiz volcano in Colombia erupted in 1985, creating a lahar which moved downhill at over 80 kilometers per hour. Over 20,000 people were killed and 5,000 homes destroyed in the town of Armero, which lay at the base of the volcano.
And lahars can also happen after an eruption if there's a rainfall afterwards. You can also get a lahar. They're nasty. So we talked about various forms of erosion. Let's talk about water. So water is essential for life. It's required to maintain our body function. About 55 to 60% of the mass of the human body is water. You are mostly made of water. The rather entertaining argument is that you are still a fish. You're just a fish who figured out how to take the ocean with you. Early civilizations flourished where water was abundant, generally in river valleys. Modern societies are also keenly concerned about the distribution of fresh water. And the global water supply is constantly in flux, being redistributed throughout the earth. It constantly travels into the atmosphere, falls down, moves around. So this is the hydrologic cycle. It's the constant movement of water from large reservoirs, oceans, lakes, to the atmosphere via evaporation, onto the land via precipitation, and eventually back to the sea via runoff. However, they can also run into groundwater and travel through the ground as well. And much of this process we can readily see as clouds, rain, snow, lakes, and flowing rivers. Now, can't see evaporation, but we can see where the water was coming from. However, a significant portion of the precipitation soaks into the soil and bedrock and becomes part of the very slowly moving groundwater system. But there's a lot of water down there, and it is still doing important things. So this is a short video about the water cycle.
The one factor that most dramatically sets Earth apart from other planets is water. Though the total supply of water has remained constant on this planet for millions of years, it never remains stationary. One of the most active Earth materials, water, is constantly moving. Its movement accounts for many of the landforms on our Earth's surface. Here in Iceland, fresh water erodes through rocks, slicing across the terrain on an ever downward journey to the Atlantic Ocean. But fresh water accounts for very little of the world's total water supply. Most of the Earth's water, more than 97%, is in the oceans. In fact, almost 71% of the Earth's surface is covered by these salt waters. Most of the Earth's fresh water is stored in glaciers near the North and South poles. In warmer weather, some of the ice melts, and the runoff returns fresh water to the ocean. Fresh water can also be found in lakes, streams, and water in the ground. The rest of the world's water supply can be found in clouds. The amount of water in the air is minute when compared to the amount of water on the Earth's surface. The clouds are formed from water evaporated from the Earth's surface and condensed as air cools. The water can then be released to fall back to Earth as precipitation. The most common form of precipitation is rain. We call this constant exchange of water between land, sea, and air the water cycle.
So that's the water cycle. For the hydrologic cycle. So if we look at the Earth's water, the Earth's 1.25 times 10 to the 18 cubic meters of water is constantly moving. The vast majority of the water on Earth is in the oceans. It's salt water in the oceans, 97.4%. Fresh water, ice makes up about 1.8% of the total water on Earth, and then groundwater and surface water is about 0.8%. So about 70% of the Earth is covered in water, 97.2% is fresh water, about 2.15% is frozen in ice caps and glaciers, and only about 0.65% is found in lakes, streams, groundwater, and the atmosphere. Groundwater alone serves as the source of half the drinking water, half our drinking water and nearly half the water used for agriculture and industry. Not around here, because we get our water from the lake, but in many places it's groundwater. Most common place to get drinking water from. And part of the issue could be that things like agriculture and industry can over extract from the groundwater. They can take water out faster than the groundwater reservoirs can replenish. So the study and proper management of groundwater resources has become one of the key environmental issues facing the world. At the present time, the human usage of groundwater is increasing each year and already exceeds the natural rate of recharge. So we are using up groundwater faster than it refills. And in most areas, these groundwater reserves took thousands of years to accumulate, but can end up depleted in only a few years. So part of this is modern agriculture is really water heavy, like excessively water heavy. We could work to make it less so. And also there's industries that use up a lot of water. And then there's like Nestle, who deals our drinking water to bottle it and sell it to you at a massive markup. But yeah, bottled water is almost entirely illegal. So in many areas, groundwater has also gotten polluted by human, industrial, or agricultural waste. This is a problem. We haven't been great about that. So the movement of groundwater largely depends on the physical characteristics of the soil and bedrock. And the two main factors that determine this are porosity, how many holes the bedrock or soil has, the percentage of the soil, bedrock, or sediment's volume that's composed of pores. So how much of it is empty space that can be filled with air or water. It's the porosity of an underground reservoir that determines the material's capacity to store water. And another important physical property of soil and rocks is permeability, which is how easily can water flow through these rocks. So you could have basically layers that are impermeable where water can't flow through, and layers that are very permeable where water flows through easily. Permeability is a measure of the material's ability to transmit fluids. So permeability of a substance is a function of how big the pores are, how abundant the pores are, and how well the pores are connected. So things like loosely packed sand and gravel have large pores that permit easy fluid movement. Mud and clay have very small microscopic pores, resulting in very poor permeability. And the average rate of groundwater flow is 14 meters per year. And then due to gravity, some of the water at the Earth's surface will slowly percolate down through the unsaturated zone of aeration until it reaches the zone of saturation. And the water table marks the boundary between these two zones. So the water table is the level at which the ground is full of water, above which there is water, but there's also air. And within the zone of aeration, air partially or completely fills the pores. Within the zone of saturation, water completely fills the pores. So the water table, if you dig down, you'll hit a point where the pores are all full of water. That is the level water will fill up to. And I will stop there for today, because we are at the end of class. So I'll see you all later today for the lab, because we have a lab today. Reminder, the chapter 22 quiz is on Wednesday. The chapter 23 quiz will be online, opening up on Wednesday and available for basically a week. And next week, in a week, on Monday, we will have our first test on chapter 1 and chapters 21 through 24. That'll be in class. You'll get a sheet of notes, just like you do on the quizzes. You will, and what else? You sheet of notes like you do on the quizzes, and it's mostly multiple choice with a few short answer questions, kind of like the quizzes. That's all for today. Sorry I went a little over, but everybody was late today. So I will see you at 1 for the lab.